All right, so let us start. First of all, let me just adjust the screen. Okay, now is the screen visible to you?
Yes, sir.
Okay, so I came to know that you have already done with the semiconductors, the concept of semiconductors, and how they are different than the conductors and the insulators, right? So I also came to know that you have completed with the p-type semiconductors and the n-type semiconductors. So just to have a recap, what do you mean by n-type semiconductor? What do you mean by n-type semiconductor? N-type semiconductor is formed with what is called as a pentavalent impurity. Okay, have you done that? Hello guys. Hello. Hello. Guys, am I
Yes, sir.
audible?
Yes, sir, you are audible.
Then please respond to me whenever I'm asking questions.
Yes, sir.
I know this is going to be a little silly kind of thing to have such a kind of session. I would have loved to have a class, online, offline class, the regular one. But at the same time, we don't have much time also. So I'm just going to use the presentation. Of course, I'm going to make some annotations over there whenever required. So N-type semiconductor. What do you mean by N-type semiconductor again? Yes. What do you mean by N-type semiconductor? Guys, come on. Hello. Why is there no response at all? Hello, am I audible? Hello. Hello, guys. Hello.
Yes, sir.
Hello. Hello. Am I
Yes, sir.
audible?
Yes, sir.
Yes, sir.
अरे फिर बोलो ना. मैं हेलो हेलो करते बैठ रहा हूँ यहाँ पे. Come on. I'm going to record all your attendance also. It's not that. Okay. So what is N-type semiconductor? How is it formed?
Sir, it is a
There's
conductor with
more
5
as
electrons.
See, first of all, you have the concept of intrinsic semiconductor and extrinsic semiconductor. When we call something as intrinsic semiconductor, means that whatever is the type, is the nature of that semiconductor which occurs in nature. For example, the silicon atom, if you look at, rather the silicon structure, if you look at germanium, those are all intrinsic semiconductors. Intrinsic semiconductors on their own, they don't have free electrons as such. Okay, there may be some electrons which are generated because of gain from the room temperature. But in general, they don't have any free electrons. Specifically at absolute zero, there are no electrons for conduction, and so semiconductor, intrinsic semiconductor, happens to be an insulator at absolute zero temperature. That I think we have already done up to that point. Right now, when we talk about extrinsic semiconductors, there are two types of extrinsic semiconductors. Extrinsic means which are artificially prepared, or let us say artificially modulated or artificially modified. Okay, kind of semiconductors. Now, the n-type semiconductor is the one where we introduce what is called as a pentavalent atom. In the sense, the atom which has got an element which has got 5 electrons in its outermost orbit is introduced as an impurity. Okay, impurity is not always bad. Impurity is used for modification of the characteristics of a semiconductor, an intrinsic semiconductor, and thus make it what is called as an extrinsic semiconductor. Now, when we introduce pentavalent atom, means there are 5 electrons in the outermost shell of that electron of that atom. For example, arsenic. Now, in case of arsenic, if you look at the outermost shell of that atom, you have 5 electrons over there. Okay. Now, when you introduce this particular atom, one atom in a lattice of semiconductor, for example, silicon, in that case, as you can see over here, that there is one electron which is not bound. Okay. Other 4 electrons will form a covalent bond just as the intrinsic semiconductor atom would have done, and this completes the valency. But there is one electron which is still remaining there. Now, if this electron is remaining there, which is unbound, it is available for conduction. Now, if it is available for conduction, obviously the conductivity of the material is increased or the resistance decreases. So we can say this process of introducing the impurity as doping. Okay, are you able to understand this up to this point, guys?
Yes, sir.
Okay, so this particular atom, which we have introduced is called as a donor atom. Why? Because it donates one electron. A free electron is available now for conduction, and obviously because of that, the resistivity decreases, or in other words, conductivity increases. Now, in spite of all this, even if we have an electron which is available for conduction, does not mean that this particular system is negatively charged. No ways. This material still is electrically neutral. Please remember this. Why? Why is it neutral? Why is it neutral? Because silicon atoms, we have already know that the protons have equal number of charge as compared to the electrons in the silicon atom. Similarly, for arsenic also we have equal number of protons to balance out the charge as far as the electrons are concerned in arsenic. So in general, the positive charges and the negative charges, so-called positive charges and the negative charges are equal. And so we can say that the material is electrically neutral. Please understand this. People think that if I dope or if n-type is negative means that it is negatively charged. No, it is not like that. Please remember that. Okay. So this is how you can modify the let us say the conductivity of an intrinsic semiconductor by making it extrinsic, and this is where the real fun starts. Okay, in a similar way, we have p-type semiconductor. Obviously, we have 3 electrons over here for the impurity. Okay, for example, boron has got let us say 3 electrons in its outermost shell, or the valence shell, or the valence orbit, and if it is introduced as an impurity in a p-type intrinsic semiconductor, you can see that there is a vacancy of 1 electron over here. Are you able to see this?
Yes, sir.
Again, what is this vacancy? We have already defined that vacancy as a placeholder for electron, and obviously absence of electron we are going to call it as a hole. So there is a possible place for an electron, and this is one electron possible place for electron is created because of this introduction of this type of impurity. This is called as a trivalent atom or trivalent impurity, and again the material still is electrically neutral. Okay. Now, why the other one is called as n-type and why this one is called as p-type? The reason is very obvious, that because of the excess electron which is available over here means that the electrons are more in number. In this atom, in this particular structure, in n-type, electrons are more, whereas in this type of structure, the holes are known. And holes are absence of electrons, so absence of negative charge, we call it as positive charge. So p type, that is the way in which the name or the nomenclature has been developed. Okay, so n type and p type semiconductors. Again, remember both these materials are electrically neutral. Okay, I hope you have done up to this point, guys. Hello.
Yes, sir.
Yeah.
Yes, sir.
Okay, so why we have the concept of majority and the minority carriers? This is very, very important. If you want to understand semiconductor physics, this is the most important part. Now, as I said, this impurity atom is introduced inside this intrinsic semiconductor, and a very, very small value or very small quantity of this impurity atom is introduced. As a matter of fact, it is measured in parts per million or billion. Okay, so it can be as small as 1 part per billion or million also. So a tiny trace of this impurity will enter the crystal, and obviously we have the N type and the P type semiconductors. So again, this is not going to be an ideal process. If you look at the atomic scale, it is not going to be possible for us to create a purely no, let us say a completely pure kind of silicon crystal. Okay, so what we have is an occasional atom with 3 valence electrons which may be present in the n-type semiconductor. It is also possible to have such a kind of contamination, let us say. Okay, it is an ideal, it's not an ideal process. So an unwanted hole will exist in the crystal, and this will be called as a minority carrier. So in n-type, we may have one atom, for example, which creates one hole, but majority of the atoms are pentavalent, and so we have what is called as the electrons are in majority over there, and electrons in n-type will be the majority charge carriers. What is this carrier? This carrier is nothing but called as a charge carrier. So we have minority charge carrier and we have majority charge carriers. This very, very small quantities of these holes will be called as minority charge carriers in the n-type semiconductor, whereas in p-type semiconductor, electrons will be the minority charge carriers. Who will be the majority charge carriers in p-type? Holes will be the majority charge carriers. Okay, is that fine?
Yes,
So
sir.
you understood the concept of minority and majority charge carriers?
Yes, sir.
Okay.
Yes, sir.
So yeah, now the real fun starts when we have a metallurgical junction or metallurgical connection of p-type and n-type material. Now, as you can see in the upper figure, n-type semiconductor, when it is totally separate, I mean it is going to behave like an n-type semiconductor. This is going to behave like a p-type semiconductor. Means that this is electrically neutral. This is also electrically neutral. At the same time, electrons are a majority charge carriers in this n-type. In p-type, holes are majority charge carriers, and so on and so forth. Of course, there are minority carriers also present over there. But now the real fun starts when we have a metallurgical junction as shown in the lower figure. So this is called as the metallurgical junction, where we actually have an n-type piece of semiconductor attached, physically connected to a p-type semiconductor. Now here the interesting thing starts happening. Now as you can see, this is the boundary. This red one is the boundary, which is the junction. And on the left side of the junction and the right side of the junction, you have different types of charge carriers or different types of material. Okay. On the left side, you have n-type material. On the right side, you have p-type material. Now what happens actually is that now when you talk about the material on the left hand side, these blue circles or blue dots, they are electrons. Over here, these white circles, they are holes. Okay, I am not showing this as an atom or atomic structure. I am showing it as a majority and minority charge carriers representation. So on the left hand side, you have electrons. You can see the blue dots or the blue circles in majority over here. Here you can see the white dots are in majority over here. And still we have some minority charge carriers over here in N type and minority charge carriers in P type as well. Now, as you can see on the left hand side and the right hand side, we have excess of electrons on the left hand side and deficiency of electrons on the right hand side. And we can see from one very interesting physical characteristic which is called as diffusion, where the charges, okay, or whenever we have the density of molecules which is very large on one side and very small on the other side, the atoms or the molecules, wherever we have the higher density, will try to equalize. They will try to go into the area where there is deficiency, okay, or there is scarcity of those molecules. In a similar way, very parallel kind of way, the electrons will try to go and occupy the places where there is deficiency of electrons. Now the deficiency of electrons is nothing but the holes, and so these electrons will occupy these holes, okay, just around the junction, okay, just above the junction. So what we have essentially is that in this vicinity of the junction, there are no charge carriers left on either side. Why there are no charge carriers left? Because the electrons have migrated onto the holes. So there are no charge carriers either on here, this side, or on this side. Are you able to understand this?
Yes, sir.
Sure,
Yes, sir.
all of you.
Yes, sir.
Let me see how
Yes,
many of you have
yes,
joined.
sir.
Okay, 44 of you have joined the class. Fine. I hope all of you are attentive because these are the basic concepts.
Yes, sir, we are.
Okay, so what essentially we have is a creation of the depletion region. What do you mean by depletion region? A depletion region is a region where there are no charge carriers present anymore. So there are no free charge carriers present in this region, which is, let us say, in the vicinity of the junction itself. Now, why doesn't this extend all the way? Why doesn't it extend all the way? The reason for that is that after a certain, let us say, extension of this region or creation of the depletion region, it is very difficult for the electron to go from here and cross this depletion region and enter into the other region. You can say the same thing for the hole also. The hole travels from here to here. So essentially, it is difficult for the electron to go from here to here. Why is it difficult, by the way? The reason for that is, as you can see, first of all, understand one thing, that if you have equal doping, that if the equal number of charge carriers are present, if equal number of doping atoms are present in N type and P type, this depletion region will be symmetric, equal number. Okay, so this width of this depletion region will be equal on both the sides. I mean, it is symmetric around the junction. Now, as you can see here, a depletion region means there are no electrons here, there are no holes here. It means that the atoms in this region, they have lost an electron. Are you able to understand this? Atoms in this region have lost electrons. Guys, is
Yes,
it
sir.
okay with you?
Yes,
Now, and atoms in this region, they have gained one extra electron, isn't it?
Yes, sir.
And what do we call an atom which has lost an electron? An atom which loses an electron is called as a
positively
negative.
charged.
It's called as a positive ion, isn't it? It becomes a positive ion. The concept of ion itself, no? The atom has lost an electron, so it is a positive ion. In a similar way, in the p-type region, the atom has gained an electron, so it becomes a
Negative
which type
ion.
of ion? Negative ion. So you have a separation, or let us say some kind of creation of positive charges on this side and negative charges on this side. We have positive ions in N-type material and P-type and positive negative ions on the P-type material. So we have a charge separation like this. So around this boundary, you have lot of positive charges here and lot of negative charges over here. Okay. And at the same time, there are no electrons. Obviously, there are no electrons and there are no holes. And that is the reason why it is called as a depletion region. So depletion region actually behaves like an insulator. But what type of insulator? The one which is having positive and the negative ions. Okay. And when you have positive and negative ions, a field will be created. Isn't it? Charge, a field, whenever we have a charge separation or positive charge and the negative charge, we will have an electric field which is created. Isn't it?
Yes, sir.
It has a field creation. And this field actually is some sort of a potential. Okay, so there will be positive here, negative here. So you'll have a positive, you'll have a potential difference here, no? Between these 2 points. And as you can see, this potential difference is maximum at the boundary. So as you can see here, this is the positive, this is the peak potential value around. So immediately if you look, if you take a voltmeter, hypothetically, if you take a voltmeter that small with those probes, and if you try to probe it, if you try to place a voltmeter across this junction, and if you measure between these 2 points immediately around the junction, you see that there is some sort of a voltage which is generated. A potential will go away.
सर आपकी वॉइस नहीं आ रही है.
Hello, guys, am I audible?
Yes, sir.
Okay, there was a call drop, so let me reconnect. Okay, now is the screen visible?
Yes, sir.
Okay, so we have already seen the concept of potential barrier where an electron starts from the negative plate. Naturally, electron will be excess on the negative side of the system, and so you have the electron starting. For example, if you provide the electron with some energy and make it leave that particular electrode, or let us say the terminal, and let us say it starts moving against the electric field and tries to go towards the positive side of the plate. But while doing that, you see that the energy, the energy that is used to move against the field at a particular point, that energy will be insufficient for it to travel further and it will fall back. So we saw that the concept was similar to what is called as a potential hill or barrier, as if the electron has encountered an invisible wall and it has turned back. In a similar way, the electrons which are on the other side of this, depletion region, they will get some thermal energy and they will try to start and go towards this, but obviously they will not be able to do that successfully because of the potential hill or potential barrier which is present due to in the depletion region. Are you able to understand this? So electrons will not be able to cross over anymore, and that is the reason why this depletion region will not extend after a certain point. Understood?
Yes, sir.
Okay. So now we have a system where we have the depletion region in between. We have N-type on one side, P-type on other side, and this is very, very interesting structure. Why? Because this is basically why it doesn't happen. So electric field at the junction, if you see, this will try to repel the electrons, this will try to repel the holes, and so it is not possible anymore for the electron to cross over into the other side. Now I have shown this positive, these red circles and this blue circles, dark blue, the positive and the negative ions over here. So it is not possible anymore to cross over into the other side. Yes, you can make them cross over provided you give, let us say, a large amount of energy to the electrons and then make them cross over into the other region. So let us now see if the doping is unequal, what will happen. So if doping is unequal, it will be seen that the depletion region is not anymore symmetric. Okay, so wherever we have heavily doped, means large number of electrons present over here, large number of pentavalent atoms in the N type, if it is heavily doped, the depletion region will not extend much as compared to the lightly doped side. You can have doping, heavy doping, light doping for N type as well as for P type, and correspondingly, because of the unequal doping, the extension or the reach of the depletion region will be more in the area where it is lightly doped. Please understand this. These are concepts. Okay. Right. So this is basically what happens in case of unequal doping. But we'll not complicate the matter. We'll just keep the doping equal and then try to understand what do you mean by the reverse biasing. What we mean by reverse biasing is that when we apply a potential in such a way which actually expands the depletion region. Means what? Means if I connect a battery with positive side or positive terminal to the N type and negative terminal to the P type. Now let us see what happens. If you connect it like this, naturally speaking, electrons which are excess in this particular region, that is the N type, they will get attracted towards the positive of the battery. In a similar way, the holes will be attracted to the negative side of the battery. In fact, what is a battery made up of? Battery is a source of electrons. Please remember this. Battery is a source of electrons. So what we have here necessarily is that these electrons, these holes are attracted towards this side, electrons are attracted towards this side, and these electrons move away from the depletion region or the junction area. And as you can see, the depletion region in fact extends more. Depletion region will extend more. Now in such a kind of situation, what will happen to the potential that was created before that? In this situation, there was a potential which was created like this. What will happen to this potential? What will happen to that? Large number of, see, the positive ions are more now here, negative ions are more. So large number of positive charges, large number of negative charges. So what will happen to the potential? Guys, the potential will increase or decrease?
Sir, increase.
The potential will increase. It simply means that the height of that potential wall, potential barrier is still more. So what we are doing is we are making this height of this potential wall or potential barrier more. And in that situation, is it possible for the electrons to cross over from here to here? Not at all. It is not possible. As it is, it was not possible in this situation. As it is, it was not possible to do that in this situation itself. And now what you're doing is you're making it worse for the electron to cross over from one region to the other region by increasing the height of the potential wall. Okay, and that is the reason why no current, ideally there should be no current flowing in this system from the positive, let us say positive to the negative side, a conventional current flow. There should be no current flow. So whenever we have reverse biasing, we don't have the current flow at all. Or in other words, this particular PN junction will act as if it is a switch which is turned off. So because of reverse bias, we are turning off the device. It won't allow the flow of electrons. But at the same time, you will see one very interesting thing happening. You have seen that there are some minority current carriers also.
Yes, sir.
So they are very few. That is the reason why they are called as minority current carriers. Now look at this minority current carriers. These minority current carriers have equal or an opposite charge to that of the electron. For example, here it is a hole. So this hole actually will get attracted across the junction, pulled across the junction. Why? As you can see, the electrons, the holes are getting attracted to the negative side of the plate of the battery. Similarly, this electron, these holes over here in this region will also get attracted and they will literally cross over because they have enough energy to do that, because the electric field is in their favor. The direction of the electric field is in their favor. Whereas for electrons, it is against them. Isn't it?
Yes, sir. Yes, sir.
So what we can say here is that the reverse bias will create a small flow of holes going from N type into P type. Similarly, electrons which are minority carriers in P type will be crossing over into the N type region. Okay, but this will be very, very small because the number of charges, number of carriers is very, very less, and so this current is very, very small. It is of the order of picoamperes. Pico का मतलब पता है ना? Pico क्या होता है?
10 raised to power minus 12.
Yes, 10 to the power minus 12. So उतना छोटा सा करंट, बहुत छोटा सा करंट फ्लो होता है in case of reverse bias. Or we can say one more thing. ये जो मैं बोल रहा था, this electric field and all those kinds of things, you can see that for this particular system, reverse bias creates such a kind of electric field which is favorable for the minority carriers. Right or wrong? Yes or no?
Right, sir. Yes, sir.
So reverse bias creates a situation or an electric field which is favorable to the flow of what?
Minus
Higher charge carriers.
Guys, here itself is a very important concept, that reverse bias will always aid, support the flow of minority current carriers. ये लिख लो. ये लिख लो. Reverse bias will always support the flow of minority current carriers or charge carriers. ठीक है ना? समझ में आया?
Yes, sir.
Any doubt, any question over here?
Yes, sir.
बहुत इसेंशियल है, ये चीजें बहुत इसेंशियल है। ठीक है, तो अभी ये हो गया रिवर्स बायस। So what has happened here is that reverse bias actually will aid the flow of minority carriers. लेकिन एक सिस्टम आपको दिमाग में, you have to always remember, keep in mind, is that these minority current carriers ये कहां से जनरेट होते हैं भैया? एक तो इम्प्यूरिटी है, एक कंटामिनेशन है, लेकिन एट द सेम टाइम ये कंटामिनेशन भी अगर होंगे तो they are also thermally generated. So minority carriers are thermally generated. का मतलब कैसा है, क्या है कि if I increase the temperature of that material, in that case more and more minority current carriers will be generated, minority charge carriers will be generated, and they will be available for conduction. So there is one more thing that you have to understand, that the minority charge carriers are temperature dependent. कौन सा टेम्परेचर? जो तुम्हारा एम्बिएंट टेम्परेचर है उसके ऊपर ये डिपेंडेंट होता है। समझो टेम्परेचर मैंने बढ़ा दिया, ये मटेरियल का टेम्परेचर मैंने बढ़ा दिया। इफ आई इंक्रीज द टेम्परेचर, व्हाट इज गोइंग टू हैपन टू द नंबर ऑफ चार्ज कैरियर्स, माइनॉरिटी चार्ज कैरियर्स?
They will increase.
They will increase. Okay, they will increase. अभी increase तो हुआ है, and at the same time you are applying reverse bias also. ये मत भूलना।
Yes, sir.
तो क्या होगा?
सर करंट फ्लो
ज्यादा करंट फ्लो होगा, है ना?
Yes, sir.
ज्यादा करंट फ्लो होगा। तो इसका मतलब क्या है? रिवर्स बायस और रिवर्स करंट जो है, रिवर्स बायस में जो करंट होता है, that will increase if I increase the ambient temperature of the material. आई समझ में बात?
यस सर।
So two important things you must have learned. One is that reverse bias will aid the flow of minority carriers, and second is these minority carriers are thermally generated. So the reverse current, whatever is the value, will be definitely affected, will be influenced by the ambient temperature. ये बात ठीक से दिमाग में उतार लेना। Alright? Okay, now if you see the forward bias में क्या होता है? What you do is apply negative side of the battery to N type and positive side of the battery, positive terminal of the battery to the P type. Now in this situation, what is going to happen? The electrons will be repelled from this side and the holes will be repelled from this side. ये क्या होगा? Electrons will be crossing over into this region in large amounts. Holes will be crossing over here in large amounts. समझ में आ रहा है?
Yes sir.
Or in other words, what we are doing is now we are reducing the height of this potential barrier by external voltage. I'll apply the external voltage in such a way that the height of this potential barrier reduces. And if this reduces to a very small value, electrons can very easily cross over into the other side, that is the P side. Holes from P side will cross over into the N side and you will see a large current flowing across the junction. So forward bias क्या करता है? It reduces the barrier potential and because of that large current flows into the device or across the junction. This is how it happens. So electrons will start moving in the p-type region. The holes from the p-type will start moving in the n-type region. Obviously, we have the current flow in the external circuit. And remember, what I have shown here is the conventional current direction. or the conventional current flow. है ना? Electrons are moving in the opposite direction. तो ये बहुत बड़ा करंट फ्लो होने वाला है. Agreed or not?
Yes, sir.
Yes, sir.
Now, if I further increase this bias, this forward bias, it is called as forward bias. If I further increase this, the potential barrier will become smaller and smaller and smaller, and ultimately it will be zero, and then a very large current will flow. It is as if somebody has turned on the switch. As if you can imagine that there is some kind of a switch which is controlled by an invisible hand. Okay, and suddenly, as if that switch has been turned on. In the previous case, it was turned off. Now the switch has turned on. And who is that invisible force who is doing it? It is this external voltage across which you are applying across the junction. Okay, so that is the reason why we say that this type of PN junction conducts only in one direction. समझ में आ रहा है? PN junction will always conduct in only one direction. Which direction? Where it has got a forward bias, then only it will conduct. Or then only it will act as a switch which is closed, which is turned on. समझ में आ रहा है क्या?
Yes, sir.
Guys, sure?
Sir.
Any doubts, any questions up to this point?
No, sir.
Okay. And that is where we create the very first component, the semiconductor device, which is called as a PN junction diode. Obviously, as you must have guessed by now, that you have this kind of device which has got P-type and N-type junction. I mean, the junction between P-type and N-type material, and such devices are called as PN junction diodes. Since it has got two terminals, it is called as a diode. Okay. Now this terminology has carried over from the previous technology, which was vacuum tube based and so on and so forth. So many things are like cathode and anode and all those kinds of terminologies have stuck together to this device as well. So which terminal is called as cathode and which terminal is called as anode? Wherever we have the N-type material, that connection or that terminal is called as a cathode, and P-type material, wherever we call it as an anode. Okay, this is the schematic symbol. Please remember that you have to get acquainted with the schematic symbols of these various different components and devices. Okay, so we have a device where now what are these black things over here? What are these black things over here? Okay, we know that this is a P-type, this is N-type. ये कुछ ऐसा structure हो सकता है, लेकिन ये क्या है फिर? What are these lines? Thick lines, black lines. These are called as the ohmic contacts or the leads. ये कंडक्टर होता है. अप्लाई करने के लिए, वोल्टेज अप्लाई करने के लिए, उसको कनेक्ट करने के लिए कंडक्टर चाहिए होता है ना. So these are all good conductors. These terminals are the good conductors. Of course, they will have their own resistance, but again, most of the times we ignore those things. Okay, so any device, when you make like this semiconductor device, it is going to have these contacts. These are called as contacts. Okay. See what is the characteristic. Now, remember that if you remember, we have seen characteristic of resistor, inductor, and capacitor. When we had the offline series lectures, we have seen the characteristics, right?
Yes, sir.
So what do you, then itself I said that okay, whenever we come across a new device, whenever we come across a new device, we study it by plotting the characteristics. And what are these characteristics? It is nothing but the behavior between the applied voltage and the current flowing through it. So that is the reason why it is called as a VI characteristics, voltage current characteristics. So in case of an ideal diode, now again I'm going back from reality to ideality just to explain that we have, let us say hypothetically I have an ideal diode. Ideal diode would be that if it is reverse biased exactly at 0, starting from up to that point, it doesn't conduct at all. It doesn't conduct at all. Whereas when it is forward biased, it immediately starts conducting. So look at this figure for ideal diode. So you have voltage on x-axis and current on y-axis. So what does this indicate? It indicates that there is zero current. Look at the current. It is zero current in reverse bias, and it has got large current flowing when it is simply forward biased. But our diode, practical diode, does not behave in such a manner. Okay. Now this, as I said earlier, when this particular current was flowing, there was a very small flow of current. Okay, that current is also called as leakage current. This current also is called as leakage current. Please remember that. So leakage current, reverse saturation current, they are all same. Okay. So we have zero leakage current in ideal diode. But in case of the real diode, you can have a look at the characteristic over here. The forward characteristic is a peculiar one. This is a more interesting forward characteristic. Let us first of all see only the forward characteristics. I am forward biasing the diode. Okay, as you can see, I go on increasing the positive voltage over here, and it does not still conduct. And at a certain point, it starts conducting. At a certain point, after some certain voltage, it starts conducting. At that particular point is called as a cut-in voltage. This is called as cut-in voltage, V gamma. Okay. Now, what do you think gave rise to this kind of behavior? Can anyone tell me?
Sir, potential barrier.
Yes, absolutely correct. So what we have here was the intrinsic, or let us say the inherent potential barrier which was created simply by forming the junction. Now to overcome this barrier, we have to have an external voltage, isn't it?
Yes, sir. Yes.
So in a practical diode, this is built-in potential. This is called as a built-in potential. And to overcome that built-in potential, I have to go in positive direction. I have to increase the voltage in the positive direction up to some certain extent, where once it neutralizes that potential barrier, and then current will start flowing in a rapid way. Are you able to understand this? So try to understand this characteristic very, very carefully. Various parts. V gamma. What is this V gamma? It is a cut-in voltage, after which the diode will start conducting. And this cut-in voltage for silicon diode, that is a diode made up of silicon, is about 0.6 to 0.7 volts. Okay, for silicon. For germanium, it is 0.3 volts. But nobody uses germanium anymore, so we will concentrate only on silicon unless and until we are faced with a specific example. So this external voltage will collapse, neutralize the potential barrier, the intrinsic potential barrier, and then after that happens, the current flow will start inside the diode. Okay. Now, what is the way in which it is governed by? You can see that is it a linear? Is it a linear equation or a linear kind of curve?
No, sir.
It is not linear. It is not linear. This is non-linear. So these devices are also called as non-linear devices. They are not like your capacitor, inductor, and resistor, where the VI characteristics are linear in nature. These are non-linear. Okay, and that is the basic reason why we have various interesting applications of these devices. So what is the equation that governs this particular curve? That is, it is given by this equation. The forward current inside a diode is equal to IS, which is the leakage current, also called as the reverse saturation current. We'll see in the next slide about this, into e to the power exponential Vd divided by eta Vt minus 1, so many amperes. So this gives you the direct relationship between the current flowing inside a diode and the voltage across a diode. See this. So if you ever want to find out what is the current flowing through the diode, once you know these parameters, Is, eta, Vt and Vd, Is of course, and Vd, you will be able to find out If. Now what is this Vt? What is this Vt? Have you studied that? Guys, what is this Vt? Hello? Hello?
Yes, sir.
What is this Vt? Basically, this Vt is called as Einstein relationship. That is, the diffusion and the mobility of the electrons are not independent. You will see one interesting thing that okay, now I cannot go back to the mobility of the electrons and the diffusion and all those kinds of things, but remember one thing. Okay, I'll put it this way. Okay, all of you know that the electrons go from valence band to conduction band when they are excited. Yes?
Sure.
Okay. Now, at the same time, this is because of the thermal energy of the ambience, basically the temperature. So if I increase the temperature, more number of electrons will be going from valence band to conduction band and so on and so forth, and then the resistivity of the material will decrease. That is the usual case in case of semiconductors. Now, it is as if I am applying some voltage. It is as if I am applying some voltage. So if I apply some certain voltage across a semiconductor, again, because of the potential difference that is being created across, the potential difference basically is nothing but the electric field, which is a force again, which I am applying. Isn't it? So I'm applying force across the semiconductor material. Are you able to understand this? Imagine a semiconductor material and I'm simply applying voltage across it. It is an intrinsic semiconductor. Please take it that way. Okay, and I'm applying an electric field across that particular piece of semiconductor. Now, because of this electric field is again the energy that I'm imparting, and this creates new electron hole pairs. Means that new electrons, more electrons will be generated by that also. So electrons will be generated from where will be generated? It will be generated in the sense it will be liberated from the bonds, the covalent bonds, or let us say they go from valence band to conduction band. Because of this excess energy that we are applying, this energy can be in the form of voltage or potential difference, or it can be in the form of ambient temperature. So thermal energy and electrical energy, both are responsible for doing this. Are you able to understand up to this point?
Yes,
Yes,
sir.
sir.
Okay, now if I want to capture the effect of temperature, how much temperature is, rather, what will be the effect of the temperature? What will be the effect of the temperature on the conductivity? That is the mobility, diffusion. That relationship is captured by this particular equation, which is Vt is equal to K into T by Q. It simply means that as if I am applying so many volts, the temperature, because of the temperature, the effect will be the similar one. So it is as if I am applying some voltage to free the electrons. So the effect of the temperature is equivalent to so much voltage, as if I am applying so much voltage. Are you able to understand this? And that is the reason why it is called as a voltage equivalent of temperature. This is going to be the most important, a fundamental quantity in your lives as electronic engineers. Vt is going to be a very important thing. Mark it very, very carefully, properly. And what does it tell you? It tells us that what is Vt? It is voltage equivalent of temperature, as if I am applying some voltage over there. K is the Boltzmann constant. T, capital T, is the temperature in absolute degree, I mean in Kelvin, absolute temperature in Kelvin, and Q is the electronic charge. So as you can see here, as I go on increasing the temperature, if I have higher value of T, K and Q are constants. So what is going to happen to Vt? It is going to be more, isn't it?
Yeah, yeah,
It is going to be more. So as if application of higher temperature means I am applying larger and larger voltage. So this actually gives us a kind of description of temperature in terms of voltage. Understood?
yes, sir.
Okay. So now what does it say? This equation. Forward current is equal to the Is. Let us not say anything about Is. Is is the leakage current. Means when it was in the reverse bias, whatever current which is in very, very small, which is a very small value in picoamperes, into e to the power Vd by eta Vt. Eta is what? Eta is an empirical constant. Given empirical means it is generated, it is derived experimentally, and it is 1 for germanium, 2 for silicon. Most of the times it is ignored. If it is not given, you have to simply ignore it. So that's going to be a constant, by the way. So if I increase Vd, If will increase, and that also it will increase in an exponential way. So this is an exponential relationship. You can see here, it is an exponential relationship. Okay. Now it is a plot of voltage versus current. So naturally, what is the resistance of this device? First of all, have you understood this equation? If is equal to Is into e to the power Vd by eta Vt minus 1 so many amperes. This is the relationship between the current and between the voltage and the current across the diode, the PN junction, semiconductor PN junction diode. All right? Yes or no?
Yes,
Okay, now
Yes,
if I
sir.
want to ever find out the resistance offered by this device, what is resistance? It will be a reciprocal of the slope of this line, no? Reciprocal of the slope of this line. But as you can see, this is not a line. This is a curve. So the resistance will be different at different points. In general, what we say is we call something called as a bulk resistance. So this bulk resistance of a diode is given by this formula. What you have to do, you have to simply go into the data sheet, find out what is V1 and I1, that is forward voltage and forward current of a diode, which is given by the manufacturer. You know what is V gamma, use this equation and find out the bulk resistance. Bulk resistance is a very good indicator of what will be the value of that the resistance offered by this device. For ideal diode, it should be 0, but for practical diode, this will be a non-zero value, which will be very, very important one. Okay, and if you look at the effect of the temperature on forward characteristics, now why will it affect? Why will the forward characteristics be affected? Because if you look carefully, you'll see this VT parameter over here in the equation, which is dependent on temperature. So changing the temperature will also change the characteristics in this particular way. VT, you can have simplification, K is constant, Q is constant, so T by 11,600, which approximates to 26 millivolts for 27 degrees Celsius. Most of the times we take this value as 26 millivolts unless and until specified. Okay, and this VT appears in the diode equation, and so temperature affects the diode characteristics. I have exaggerated it over here, but then the curve literally shifts on the left hand side as I increase the temperature, meaning that d by dt of Vd, that is voltage across the diode, decreases by 1.8 millivolts per degree Celsius. This is what you have to really keep in mind. All right, guys, have you understood this? Hello.
Yes, sir.
Yes, sir.
Yes, sir.
We have run out of time, so I'll stop over here. All right. Any doubts, any questions up to this point?